Now I'm going to start screen sharing. Okay, so Unit 1, functions and exponents. So in our first unit, we're going to be dealing with these two things just to kind of rehash some of the things that hopefully you've retained since Math 1 or previously. Functions are basically some sort of equation that's going to be visually represented on a coordinate grid. And specifically, functions are like a certain family of those graphs. Namely, they're going to pass the vertical line test. So the good news there is that we're not going to deal with anything super crazy as far as equations goes. Nothing's going to like loop back around on itself or do nonsense stuff. We're going to deal with a very specific family of what we call simple functions. Okay, and so that's what that means. We're going to deal with exponents a little bit later in this unit, specifically how like they're graphed and that sort of thing. You have been introduced to this in Math 1, hopefully, so we'll revisit that as well. But our first section is about one of those family of functions, and that's called the absolute value function. Hopefully, you are familiar with what absolute value does. It is a math function. It is a math operation, rather. And simply put, whatever is in these absolute value bars, it's going to spit out the positive version of that. Okay, so it's not very exciting, but if you have a positive number and you take the absolute value of it, it stays positive. It really does nothing. So the absolute value of positive 5 stays 5. Okay, absolute value of 17 is 17. Nothing really crazy there. A negative number, that's where at least something interesting happens, where if I take the absolute value of a negative, it spits out the positive version. Okay. Mathematically speaking, what is an absolute value? It's actually the distance away a number is away from 0. So how far away is 5 from 0? It's 5 away. How far away is negative 5 from 0? It's also 5 away. It just happens to be on the opposite side of the number line. Okay, so that's what absolute value does. Hopefully you're familiar with it. For our intents and purposes, namely for graphing the functions, what you'll be asked to do throughout this section, you're going to be concerned about what does an absolute value look like, not like what it looks like in terms of the actual operation. I'm talking about graphically, what does an absolute value function look like? And in short, it looks like this. It looks like a V. Okay. Now this is what we call a happy face version of an absolute value function. It's happy face because it's pointing upwards. Okay. But it is possible for that V to be pointed downwards. Okay, that would be a negative version of the absolute value function, and that just happens when I have a negative sign in front of the absolute value bars. And we'll visit that in this section as well. But that's one of the main punchlines to pull out of this section is what does an absolute value function look like? It's a V. And if generally you know what it should look like, it's a quick mental check on like when you're working through your problems. Does my absolute value function look like a V? If not, I might have done something wrong. Okay. The other feature to be aware of in an absolute value function is the interesting part of the graph, namely what makes it a V. It's this little corner, this little reflecting point. Okay, we call that the vertex. Vertex literally means corner. Okay, and so the corner of my absolute value graph, that's going to be the interesting part of my absolute value function. The reason why it's the interesting part is if I chose to graph this absolute value function, and like if I take this window and slide it over somewhere else, it would just look like a line. So if I were to like cover that up, that just looks like a negative slope line. If I were to cover up that end, now it just looks like a positive slope line. For an absolute value function, I'm going to be very curious where this vertex is located. Okay, and one of the formulas that we're going to learn a little bit later in this section is going to deal with how can I identify where that's located within the actual formula. And so I'll get to that a little bit later. Okay, so I'm going to step back from these notes for a second, just do a quick review from Math 1, just to revisit us on those functions. Okay, you should be familiar with these two functions so far. These are two things that we've learned through Math 1. Namely, you should be more than familiar with this guy. You probably had to do a lot of stuff with linear functions at the middle school level or at Math 1 level or both. Okay, y equals mx plus b, that's what we're familiar with, and we're going to get a straight line. Okay, features about this formula will tell me information about where this line is located on a coordinate grid. okay? Namely, this M is going to tell me the slope of that line. This is actually what makes a line, okay? The slope is the rise over run between any 2 points on that line. And B represents the y-intercept, or how far vertically up or down this line is moved. Those two features dictate where this line goes on a coordinate grid. Exponential functions were a new addition in the Math 1 curriculum, where this is the second function that you've really learned, the exponential function. Obviously, it looks a little bit different. Lines are linear lines, right? Exponential, curve. The way I described it to my students is that this was like a banana shape or a boomerang or a water slide, whatever works for you, okay? But you're gonna get this curve, this acceleration, this growth or decay that happens over time, okay? And if you were a student in my class last year, we talked about how with disease, very appropriate these days, I suppose, with the spread of a disease, they tend to have exponential growth, okay? As one person gets sick and they get other people sick, they in turn get more people sick, it grows exponentially. Basically, instead of adding the same rise and run every time, you're multiplying the growth over time based on how many people are infected or how whatever is spreading or decaying. Okay, but obviously we get a different look in the equation as well. That's why it's called exponential, because my x is in the exponent spot. And now the third family is absolute value. And absolute value, again, has a signature look. We just talked about it. It will either be the happy face V or the sad face V. Both of these are absolute value functions. And the equation that will be the parent function for these, kind of the most basic form of what you'll be looking at, is absolute value of x. This is a happy face version of the absolute value function. The sad face version is a small change, but a significant change. And that's when I have a negative sign in front of the absolute value. Why did that matter? It turns everything upside down, because even though an absolute value makes anything positive, what I've just done is whatever is in here turns positive, I just turned it back negative with that negative sign. So when you see a negative sign in front, you're going to get a sad face V. Okay? So that's our family of absolute value functions. It will be a V shape, and we'll talk about how that shape can change depending on the formula that you're given. So let me get back to the notes at this point. Flatten this off. All right, so in the notes, these are the things that you're going to be seeing on your assignment, what you might see on a Chapter 1 test. You're going to be given various functions to graph, simply put, right? And this is going to be a theme in this unit as a whole, is we're going to be dealing with, here is a function. This will visually look like something on the coordinate grid. Your job is to map that out. Basically, pull out what the visual is from this equation. Or vice versa, here's a graph. What is the equation that makes that graph? That tends to be the two ways that you're going to see things in Math 1, 2, or 3, the progression as you get through high school. Okay, equations are going to be mapped to visual graphs. Visual graphs can be mapped right back to some equation. Okay, and so interpreting that is really what these first algebraic classes are about. So you're going to see variations. And just one thing I want to remind you about, when you are given something where the instructions tell you to graph. And in my notes, the notes that were uploaded onto Google Classroom, you were given several examples that you were asked to graph various functions, okay? However complex they may be, okay? Default, what you can always do if you're ever asked to graph anything and you're given an equation, is making an XY table. Okay, this is kind of the foolproof way to figure out what visually it looks like. Basically, what does an XY table do? You pick a bunch of X values, you get to pick what values you choose, however complicated or however easy. You throw them into the equation. So if I chose X equals 0, I would plug in 0 for X and basically just do the order of operations and try and figure out what pops out the other side. Okay, that's what XY tables are about. If you throw enough X values in that spit out different Y values as a result, you're basically creating a series of coordinate points that if you graph them, you're visually seeing what the equation is doing. So let me slide over to the solution set. These also are on Google Classroom. Okay, these just reduce those notes down to just their examples. So I just wanted to kind of walk through what exactly is happening in these. Let me do that first example right here. So this was, we're given g of x is equal to the absolute value of x plus 3. This again is some function. This is an absolute value graph. I know it's an absolute value function because the absolute value bar is inside of the actual equation. And that means I know it automatically should look like a V. Wherever that V is located, it should be a V somewhere, okay? And so this function visually will look like something. And in your assignment, you're gonna be asked to graph that something. How do you figure out what it looks like? XY table, all right? Now, on these solutions, the ones that are up on Google Classroom, I've shown more work than you probably need to show, okay? I go pretty in depth. I show all the steps, mostly so that it's a little bit easier to interpret, okay? So as you're looking through the solutions, hopefully they're clear enough. If you do have questions, feel free to email me or ask me after the lesson. But how did I come up with these X value numbers? You could have chosen something entirely different. Typically on big ideas, they're gonna want 5 coordinate points. And the reason why they want 5 is because it's enough information to create the V on both sides, okay? That's typically what they're gonna want on big ideas. Same for my tests. So how do you choose what values to pick? Technically you can pick anything. As long as you are able to show where the V is located, you'll be fine. I'll talk a little bit more about how to locate where that vertex is in just a second. But create an XY table, pick some X values. My suggestion, pick some positives, pick some negatives, pick 0, keep things kind of simple. These just generally tend to be the most basic ones to throw into the equation. And all you're doing is step at a time, if X equals 2, plug it into your equation, do your order of operations. So when I plug in 2, the absolute value of 2 is 2 again. 2 plus 3 gives me 5, okay? What I've just created is a coordinate point. So visually, plugging in 2 gave me this coordinate point, 2, 5, okay? And so 2, 5 would be right there. That's just that single point. Obviously, I need more information to graph it than just a single point, so that's why you finish out your XY table, okay? And another thing it's gonna ask you about is like, how did the absolute value shift around? In this case, it took the generic absolute value V and it shifted it up 3, okay? And I'm not gonna go super in depth right now for time's sake, but you're gonna do the same thing for no matter what kind of equation you're looking at, no matter how complex or how simple. You're just basically throwing X values into this function, seeing what pops out the other side. You've just created a coordinate point. So when I plugged in 2 into that first equation and 5 was my result of plugging in 2, I've just created the coordinate point 2, 5. When I plugged in 0, 3 popped out the other side. That's another unique coordinate point on that graph, okay? You do that enough times and you've got your graph. But let me jump ahead to the end of this lesson where I'll start to wrap it up because I wanted to address the most complicated part of this section, and that's this vertex form of the absolute value. So this one obviously is a lot scarier looking, okay? There's a lot more happening in this format. Namely, for this example right here, we see a lot more complication going on. Each of these numbers does something to the shape of that absolute value V. It's just learning how to interpret it. And this is really more of like a shortcut. Default, what you can always do if you were given this and asked to graph it, again, you can just throw a bunch of X values at it, do your order of operations, calculator work, and see what pops out the other side, and visually you'll get what the graph looks like, okay? So here's how you can interpret it. I'm gonna jump to the more critical part of this, namely this piece, the vertex. So in this form, it actually tells you where the corner of that V, that vertex, is located. It's at this HK, all right? And what is HK? HK are gonna be the numbers inside of the absolute value and the one that's added or subtracted outside, not multiplied, these two guys, okay? If you can interpret where this is, as soon as you know where that's at, wherever this number is specifically, this H, you know exactly where to center your XY table, because that will tell you exactly where the corner of your vertex is going to be, where the corner of your absolute value V is going to be. So looking back at these other examples, I'm just going to quickly interpret where each of these H's is going to be for each of the examples. Okay, so again, what I'm looking for in this case is what number is attached to X inside of the absolute value. I'm going to care about one thing. When does this absolute value go to 0? Okay, when does it go to 0? Because that's going to represent the reflecting point. In other words, it's going to tell me where the absolute values went positive to where they should have gone negative, but instead reflected back. Okay, so in this case, on that very first example we did, there's nothing inside the absolute value except for X, which means technically there is a number. That number just happens to be 0. Okay, so that's the same thing as saying absolute value of X minus 0. In other words, where should my corner be located? At X equals 0. The second example, now I have a different absolute value function I'm given. Inside my absolute value bars, I have X minus 2. Okay, X minus 2. That X minus 2, I'm looking for where does this go to 0? What value of X makes this go to 0? The simple way to think about it is just the opposite of the other number, positive 2. Okay, at positive 2, 2 minus 2 goes to 0. That tells me the corner of this, the vertex of this absolute value V is at positive 2. In other words, if I were to go to the right 2 on this coordinate grid, I'm going to find my corner of my V somewhere on there. Does that make sense? Moving on, if I had something like this, again, just like on that first example, there's nothing inside the absolute value, so technically the corner is located at 0 again. This one, same thing. Nothing's inside the absolute value. My corner is going to be located somewhere at X equals 0, somewhere along that Y-axis for each of these. This one, as complicated as this looks, again, I'm just looking at like what's inside with the absolute value. What value makes that go to 0? The opposite of the negative one right there, or just 1. So in other words, if I were to go to the right 1, this one would tell me where the corner is located. Okay? So those are just some of the shortcuts. This combination here will tell me where the actual corner is located. What about this little K out here outside of the absolute value? That tells me how far up or down the corner is located. This one is how far left or right. That one's how far up or down. Together, they give me an actual coordinate point for that vertex. Okay, and for the sake of time, I'm going to kind of end it right there. If you need a little bit more tutorial about how to interpret this guy in terms of graphing it, locating a vertex, and figuring out how to interpret those, feel free to email me or just talk to me during office hours. But for right now, that will be the end of the lesson. I'm going to stop sharing, and I'm going to end the recording.